In an electric circuit, resistors can be arranged in two different ways. We can have resistors in series or resistors in parallel. So this is just a refresher because at this point you should be used to arrangement of resistors from your basic physics. Okay, so but in this discussion, we're going to highlight a few more things associated with resistors in series and resistors in parallel. A very quick glance, all right? Before diving in here, there are two fundamental ways to connect resistors in a circuit, all right? Resistors can be connected in series or in parallel. When we say resistors are connected in series or in parallel, let's see a very quick comparison. For series combination, components share the same current path. Current must flow through every resistor one after the other. For parallel combination, each component has its own separate current path, all right, between the same nodes, all right, between the same two nodes. Okay, so what we are saying here is that when resistors are in series, no matter how they appear physically or on the diagram, once the same current is flowing through all of them, it means they are in series. And then in parallel, the current divides among them. Okay, now the total resistance increases as more resistors are added for series connection. And then for parallel connection, the total resistance decreases as more resistors are added. It is always less than the smallest resistor. Take note of this point. Okay, so if I have resistors in series, for example, maybe I have R1 and then I have R2, I have R3, just like that, like that, like that. This is R1, R2, and R3, all right? So the total resistance here is going to be the sum of all these resistance values. So as I add more resistors, all right, the total resistance will increase. But if it's a parallel combination, as I add more resistors, the total resistance will decrease. If one resistor in series, all right, has a problem, that means the entire circuit is going to be affected. That's for a series combination. But for a parallel combination, if one of the parallel resistors has a problem, the other ones will still keep working because the path through which current flows through them differ. Okay, so this is typical of how a series combination looks like, right? Sometimes in your circuit diagram, it might not be as straight as this, all right? You can have a situation where you have, maybe you have a resistor like this, then you now have something like this, you have something like this, you have something like this, you have something like this, then you have, this is not looking as if they are on a straight line. But if you check out all these resistors here, if current is entering from this point, there is no other path that current is going to follow. The same current that enters through this resistor, let's call this one R1, all right? Let's call this R1, and let's call this R2, and let's call this R3. So the same current that enters through this goes this way, goes this way, goes this way, and then comes out through this place. So between these 2 points, now let's say point X and Y, if we want to consider the total resistance, they are in series because there's no other path, all right, that tends to divert the current coming in. So when all resistor values or when all resistors are in series, the same current flows through them, irrespective of how they are arranged in a circuit. Once the same current can flow through all of them, they are in series. Okay, now this is a typical diagram or a simplified circuit that shows resistors in series. Here you have R1, R2, and R3. And then you have a battery connected across. Okay, so in series, current is the same through every resistor as I've explained. Voltage is shared. All right, so voltage is divided when resistors are in series. That is another point to take note of. Current is the same, but voltage is divided. So another name for resistors in series, all right, is voltage divider. Voltage divider. All right. Resistors in series are also known as voltage dividers. Let's write that properly. Voltage dividers. We're going to see why we call them voltage dividers shortly. Voltage dividers. All right. They are called voltage dividers because they divide the voltage that feeds the circuit. Okay. Now, same current, voltage divides. All right. Resistance adds. Every resistor, increases the total resistance, and then Ohm's law applies to the whole circuit. All right, and to each resistor individually. So if you have resistors in series, this is your battery. Current is flowing conventionally in this direction from the battery through these resistors. So this current flows through R1, R2, and R3. All right. Now, this current, when it gets here, we can apply Ohm's law here. We can say that the voltage through the first resistor for V1 now, we can say is equal to I multiplied by R1. For V2, we can have it as I multiplied by R2. And then for V3, I multiplied by R3. All right, V3 is I multiplied by R3. So the same voltage, the same current passes through them, but their voltage is going to be different. They are going to divide this voltage that is coming in. That's why they are called voltage dividers. Okay, let's take a very simple example to explain this point. You have a situation where you have 100 ohms, 220 ohms, 470 ohms, all arranged in series as shown. Okay, let's write this symbol very well. So that's the battery symbol. Okay, so here, this is going to cause current I to flow in this circuit. And because they are in series, the same current is going to be flowing through them, no matter what. So if we want to get the total current flowing in the circuit, we have to get the total resistance. And for resistors in series, the total resistance is the sum of all the resistors. Okay, you sum all the individual resistors. All right. So by the time you sum them, the total resistance here is going to be equal to 100 plus 220 plus 470. And that gives you 719 ohms. So if you apply Ohm's law, okay, applying Ohm's law, V be equal to I R. R is the total resistance now. Like we stated in the previous slide, that Ohm's law applies to each resistor. All right. Ohm's law also applies to the total circuit when you have the total resistance, when you have the sum of all the resistors together. All right. So if you are dealing with the total resistance, you can apply Ohm's law. If you are dealing with individual resistance, you can also apply Ohm's law. Okay, so V in this case is 9 volts. So we can have it that the current flowing now is equal to V over total resistance. That gives you the total current supplied. And because this is a series circuit, the total current is going to be, the same for all the resistors. Okay, now we can now apply Ohm's law individually to this, and to this. If we apply Ohm's law individually, that means for the first resistor, let's call it V1. All right, V1 is going to be equal to the current flowing multiplied by R1. The current flowing is still the same current, I. So by the time you do that, I, all right, if you calculate I, you're going to be having this value, total current, 0.01139 amperes. If you convert that to milliamperes, that's like 11 milliamperes, all right? I'm sure that conversion is a simple thing to be done, all right? So by the time you now apply Ohm's law individually, you can now get the individual voltages that drops across these resistors. So if you do that for V1, you're going to be having I multiplied by R1. That will give us the current is 0.01139 amperes multiplied by R1, which is 100. That will give you 1.139 volts. All right. So this is voltage drop across the first resistor. Do the same thing for the second and third resistors. You're going to be having the voltage drop across them each. So what you observe now is that these resistors have succeeded in dividing the voltage, all right, that supplies the circuit. And by the time you sum everything together, you're going to be having the total voltage that also supplies the circuit. So this is why they are called voltage dividers. All right. The take home here or the takeaway here is that for resistors to be in series, all right, the same current must flow through them, but the voltages across them are going to be divided. Okay, and it doesn't matter how they are arranged on the circuit diagram. Once it is the same path, all right, the same current that flows through them, they are in series. Okay, for parallel resistors, they share current. So in parallel, voltage is the same, but current is divided. You can see the comparison between series and parallel um, combination now. And then for a parallel combination, your total resistance is given by this equation, which you should be very familiar with at this stage. So if you have parallel resistors, that means you can have a resistor in this manner. Um, let's draw something straight. Okay, and then you have a resistor there. Then you have another resistor. Let's put it this way. Okay, and then you have this, and then you have that. Beg your pardon. Let's draw that properly. So this is one resistor. Then maybe you have this. Then you have this. Then you have this. Then you have this. Okay, I'll just take a case of two resistors. Okay, you can see here you have R1, R2. So any current that is coming into this configuration is going to be divided among these resistors. And you can have any number of resistors in parallel. So irrespective of how they are arranged in a circuit or how they appear on your diagram, once they don't, once they share current, they are in parallel. That's the secret to decoding resistors in series and in parallel. Because sometimes the way your circuit diagram appears might be a little bit confusing. Okay, so for parallel combination, the voltage is going to be the same across the resistors, but the current is going to be divided. All right, so for that reason, we call them current dividers. All right, resistors in parallel are known as current dividers, while resistors in series are known as voltage dividers. Kindly take note of that. Okay, then for parallel combination, the total resistance is lesser than the smallest resistor. What that means is if you have um, three resistors in parallel now, take for example, you have 3 ohms. This is just an arbitrary example. You have 5 ohms, then you have maybe 7 ohms, and they are in parallel. By the time you take the total resistance, all right, of this combination, okay, the total resistance based on this formula now, if you take it, it is going to be smaller than the smallest resistor there. Very important to note. Okay, so let's look at some examples. If you have 3 resistors, I beg your pardon, these 3 resistors, I beg your pardon, in parallel, it's simple. You apply the formula 1 all over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And then you simplify. So that means 1 over RT is going to be equal to 1 over 120 plus 1 over 60 plus 1 over 40 plus 1 over 40, right? So this is a simple mathematics. By the time you do that, you're going to have RT as 20 ohms. And once you have gotten RT, you can apply Ohm's law. V is equal to, you know, IRT to get the total current. So I is equal to V over RT. If you are given what V is, you can get your total current supplied to the circuit. Now, for a series combination, we said that the total current is the same current that flows through all the resistors. But for a parallel combination, this total current is not the same current that flows through all the resistors. This total current becomes divided among the resistors. Okay, like in this example I cited here now, in this simple diagram that we had here, if this is maybe R1 is equal to 2 ohms here, and then R2 here is equal to say 4 ohms. This is just a simple example. Let's wipe this. And then maybe these resistors are connected across a supply. Let's take this just to just illustrate. Okay, if they are connected across the supply in this manner, let's draw that more neatly. Okay, and you have this, and then you have this. Let's assume this is um 8 volts, for example. There's going to be current flowing from this resistor, from this voltage source, like because of this voltage source, current I. If that current gets to this junction, okay, it's going to divide. This current that is flowing will divide. So this is now the total current. The total current is gotten from the total combination. And how do you get your total combination? You apply the formula 1 all over RT is equal to 1 over R1, which is 1 over 2 plus 1 over 4, right? This can be for any number of resistors in parallel. I'm just taking 2 as an example to illustrate. So 1 over RT here is equal to 4. We have 2 plus 1, right? Let's be sure about that. This is 4, 2, 1. Okay, so we have it as 1 over RT. This implies that 1 over RT is equal to 3 over 4, right? 3 over 4. 3 over 4. Which means that RT is going to be equal to 4 over 3. 4 over 3 ohms, right? So if I want to get the total current now, I apply Ohm's law by saying V is equal to IRT, right? And then V now, I is going to be equal to V over RT, which is equal to 8 divided by 3 over 4, right? So whatever I get from here gives me the total current. But this total current, by the time it gets to this junction, is going to divide among these resistors. That's the peculiarity with, resistors in parallel. Okay, the voltages are the same. So this 8 volts is the same for the 4 ohm resistor and the 2 ohms resistor as a matter of principle, all right? So if I want to get the current through this, I can just easily apply, let me just call this one I1, let me call this one I2. If I want to get the current across each of the resistors now, once I know that the voltage across them is the same thing, I can apply Ohm's law individually there. I can say I1 is equal to V over R1, and I'll get the current for that resistor. I can also say I2 is equal to V over R2, and I'll get the current for that resistor. So that's going to be equal to 8 over R1. 8 over R1 is 2 amperes. 8 over 2, sorry, 4 amperes. 4 amperes, right? And then I2 is going to be equal to 8 over 4. 8 over 4, and that's going to give us 2 amperes, right? So by the time I add this current now, it will give me the total current, which is going to be equal to 6 amperes. Now, apply this formula here. If you want to get total current directly, if we apply this formula here, this is like saying 8 over 4 over 3, right? That will give us 8 times 3 over 4. All right, so that's going to give us 6 amperes. So you can see the total current here is 6 amperes. When we calculate the total resistance and use it straight to get total current. All right. But here, if we calculate the currents individually and add it up, we're still going to arrive at 6 amperes. Okay. So you can have a combination where you have a mixed resistive network, a combination of both series and parallel in a single network. And that's going to be what we shall consider next.